Hello and welcome. Let's start with our lecture on general theory of relativity. This is a part of course PH4205 at IISER Calcutta. So this is basically an introductory course. Today being the first lecture, let's start with the very basics. Let's try to see the beginning of relativity, especially from the Galileo's and Newton time, and then go on to Einstein's theory of relativity. So we'll start with some of the very basic things which you all know very well, but it need to be covered for the sake of completeness and also to give the proper perspective of coming lectures. There are some of the mathematical aspects which need to be very clear for the elementary subject, and that get only complicated as we go along. So let's continue with our lecture. So we are going to learn about general theory of relativity. This is especially an introductory course. This lecture is essentially dedicated to Newton, who is first to formulate the entire idea of mechanics and laws of gravity, all combined. Today we call it a general theory of relativity. Newton's mechanics is one of the foundations of physics, and related idea is further developed into theory of relativity. This is a part of course PH4205 at IISER Calcutta, and my name is Rajesh Nayak. What is the theory of relativity? The idea of relativity goes way back to Newton or little further back to Galileo. At the time, the goal of Newtonian mechanics was to explain the evolution of things, that things evolved and you basically wanted to understand. The thing could be a small grain of dust to entire universe itself. So that is a basic idea of Newtonian mechanics. Newton idealized the problem further and divided things into smaller units, hoping to put everything together. So the smallest unit he called a particle. So that is a basic idea, that you divide everything and study the smallest unit and then put things together. An influence that changes the particle's evolution was called force. When the force is acting on a particle, it changes its state, and that is what you are going to study in the Newtonian dynamics. So let's look at the Newton's laws of motion. To study interaction between the particle and forces, Newton set up a stage called the inertial frame. Before starting with the exact Newton's law, Newton first formulated the stage, and that is called the inertial frame. Here, Newton basically used the Galileo's idea. Galileo has actually formulated the concept of inertial frame. Galileo had well studied and well documented, and this now is called the Newton's first law of motion. An inertial frame is a system in which a particle at rest or moving at uniform velocity remain in the state in the absence of any forces. So this is a well-known definition which you have all studied time and again. Newton's first law says that in absence of force, if the particle is remain at rest or moving at uniform velocity, which will continue to do so. So that is basically assumed as a test for the inertial frames, and later on which you can define the Newton's laws of motion. This condition can be used as a test from inertial frame. Whether given a system of reference or a stage is an inertial frame or not, you can test using the Newton's first law of motion or Galilean principle. So all you have to do is to go to the frame and keep a particle at rest and see whether it is continued to remain at rest, and put a particle in motion and see whether it is going to move at a uniform speed. If that happens, then you call it an inertial frame. If that doesn't happen, then it is not inertial frame. Let's have a look at some of the examples. These are very standard example. First thing to check is the room in which we are sitting is actually an inertial frame or not. So we have to do this experiment. All we need is a table and a person who could do this experiment. So all you have to do is leave a particle at some stage and see whether it remains. Of course, in your room, if you leave a particle, it would naturally drop. That is because of the gravity. Earth's gravity pulls it down, and that makes the frame is not inertial. In full 3 dimension, the room around or a small region on the surface of Earth is not an inertial frame. However, we all know that when we restrict it to 2 dimension, that is horizontally, when we have a 2 dimensional plane, such as the top of this table, can be assumed to be inertial. This we can check. We can keep a well-balanced table such that it is completely horizontal and leave a particle at there, and it will continue to remain at rest. Or if you try to move it at uniform speed, it will continue to go at uniform speed till it falls off the table. So this is to show that a perfectly horizontal 2 dimensional surface on the Earth is a inertial frame. This is what basically most of the experiments have been done on the table, where everything being support and you have a inertial frame. Now let's go ahead and check some more frames. One of the most popular one is the rotating frame. Here you have a large circular table, not necessarily to be circular, which is rotating about axis orthogonal to its plane. In this frame, you want to check whether it is an inertial frame or not. These are very simple ideas which you are very familiar with and already studied. I am just giving it for the completeness and continuity. So what happens if you leave a particle center of this disk? Nothing is going to happen. It's going to remain there all the time. Nothing is going to happen. That doesn't mean that it is an inertial frame, and we got to keep it in another frame of the center somewhere else, and then you will see that slowly it will drift off because there is an unbalanced force which you are all familiar with, which is called the centrifugal force, which is taking the particle away. So this frame is a classic example for the non-inertial frame where interesting effects begin to happen. Einstein is supposed to have spent a lot of time studying the rotating frame as an example for non-inertial frame. He basically calls it as a missing link between the special theory of relativity and general theory of relativity. Of course, nowadays full theory is formulated and nobody has the time or energy to study the rotating frame. It is a good example. We will see it whenever and wherever needed. Let's continue with the Newtonian mechanics or Newtonian dynamics. Once you are ensured that the system in which you are doing your experiment is an inertial system, then you can go ahead and apply the Newton's law or Newton dynamic, which is basically given by the force acting is equal to rate of change of momentum of the particle. This basically tells how the force and momentum interact with each other. Particle has a physical property which we call as a momentum, or which describe the state of the particle, which would be continuously changing in presence of force. In absence of force, it would not change. That is what we have already verified using the Newton's first law of motion. The force usually called a vector field. Vector field means which has a both direction and magnitude. That is a simple way of seeing, but I am sure you are all full familiar with the notion of vector space and continuous vector field. So the force is essentially represented by vector field, and the momentum is also a vector field, and the Newton's law essentially relates between these two, and that is what we have is a Newton's laws of motion. Now for a simple particle, we can usually write the momentum as a mass into velocity. Velocity is another vector, mass is a scalar. So Newton, here it is important to see that the mass is the coupling between the force and the velocity of the particle. This is where the interaction happens. If the mass is zero, as per Newtonian mechanics, there is no interaction between the particle and velocity. Of course, Newton did not formulate anything with the zero mass particle, that idea which comes much later. However, it is clear to see here that mass is a fundamental quantity which couples the force and the velocity. And if the mass is absent, then there is not going to be an interaction between the force and the velocity. So what basically have is a particle, which is represented by its velocity, initial velocity you have a force field present around that. When the force is influencing the particle, then particle trajectory would change, and that is what we are planning to predict. So what we have is a Newton's equation which equates the force and the rate of change of momentum, which we write is a mass into velocity. Then we can write the velocity as a rate of change of position vector of the particle, and then we have a force is equal to mass into second derivative of the position, that is what we call the acceleration. So this way we have force is equal to mass into acceleration, which is basically tells us how particle would behave in presence of external force whose acceleration would be changing, and by solving this equation we can obtain the position of the particle at all the time. So that is basically idea of Newton's second law of motion. So this is what helps us to solve the problem of mechanics. Now rest of the all the things, it looks like basically application of this simple law. For 300-400 years people have been doing it. You have various different forces, and then you have initial velocity, and then you predict the trajectory of the particle under various circumstances. All the change, position, momentum, all are referred with respect to time. So the Newtonian mechanics had a very simple idea of time, what we call is global time. There is a single time for the entire universe and for all the observed. Time does not change from place to place or people to people, so it's an eternal entity. So all we have is you can carry a clock and everybody would have a same set of measurements. This is a very interesting idea, but very simple. We have seen as a time as a evolving in the eternally going in the background, uniformly going in its own way, and you can have a various observers who could carry their own clock, but it will be always be matching with the eternal time. So we can have a various inertial frames, and then they will all have a same time. It's all look very funny now, but however, long time, this was a basic idea of time, that it is the same for everybody. You are not allowed to fiddle around with the time interval is same for everybody. So for example, you cannot have a time axis something like this, which is slightly rotated to your original inertial frame. This would leads to a different rate of clock, may be constant again, but still a different rate, which is not allowed. So time axis cannot be played around. It is fixed, uniform. No rotation allowed, nothing is. So this is basic idea of Newtonian time. So once we have this framework of absolute time, we can measure everything with respect to this time, and that is what we call is a change in configuration or evolution with respect to this time, and that is what we study. Now let's quickly look at it's time to do some practical thing. Let's quickly look at the vector space in Rn, which plays a very important role here. You have seen that n here is 3, but it does not harm to talk. N in general is like a big show off that we are doing n-dimensional thing. However, you can put that n to be 3 or 2 or 1, whichever convenient. I'm sure you already know that Rn act as an n-dimensional vector space. It's too late to go over all these things. I believe you have already studied. The standard Euclidean basis in 3 dimension is given as E1 is equal to 1, 0, 0, 0, and E2 is equal to 0, 1, 0, and E3 is equal to 0, 0, 1. You usually call it as a EX, EY, EZ. So we try to avoid that. We call it a E1, E2, E3 so that we can use them in n dimension, as well as not bothering to put the symbol X, Y, Z, and so on. So these are called Euclidean because they are all orthonormal, and they form a distance given as a simple x square, y square plus z square. Any vector can be expressed as a basis element, and that is what we know from the vector space. That is, if f is a vector, then it should be able to expressed as a linear combination of basis element ei with the coefficient fi. That is basically property of a vector space with the basis. So in our case, the basis is given E1, E2, E3. So idea here is that you have a first basis geometrically given as a E1, and the second one is E2 in 2 dimension. You could have an arbitrary vector F whose component in the direction of E1 is F1 and component along basis E2 is F2. So this is a very trivial. You can find the component of that vector by taking the dot product of the vector with the basis element. That would simply give you the component. So this is a very elementary vector algebra. So let us try to use this in the Newton's law. So we again have a Newton's dynamics. We write the Newton's law as force is equal to mass into rate of change of velocity. Either you can call it a momentum or velocity. I seems to have messed it up, right? So both force and momentum are vectors which can be written in terms of the Euclidean basis E1, E2, E3, and simply we can do it in both ways. We can express them as a basis element as a linear combination, or we can simply take the dot product of the Newton's equation with the given basis to obtain the component. So then we end up having a F is equal to m into dv by dt. Now here several things have gone in. One of the important thing which has gone in is the bases themselves are constant and orthonormal. That means d by dt of ei's are 0, and that is what helps you to pull out e from the differentiation, and then you write. You can further go ahead and write this equation as f is equal to m into d square x by dt square. So this is a component equation of Newton's law of motion. This form of Newton's law is very, very popular, as we often fond of handling the component rather than the vector itself. So that is a convenience of using orthonormal basis. So this is what essentially how the calculation progresses in terms of vector space or in the. Let's come back to this little later and give a geometric interpretation. So this is a nice form of Newton's law we have. Let's try to make it little complicated at this stage. Let's try to see if we can apply a basis which are not constant. You can have bases themselves as a vector spaces, and they could be changing from place to place. One of the example is the spherical polar coordinate system, in which if you are expressing the vector, there you know that the basis vector would change from point to point. But we will come back to this in more detail because that's a main crux in the Riemannian geometry. But let's have a look at the Newton's law again. Let's say that the force is equal to rate of change of moment. Now let's write down the force and the momentum in terms of basis ei. I goes from 1, 2 and 3. Now here one thing which we do is we assume that the ei's themselves could be changing either from point to point or with the time. In both cases, if we write down the Newton's law, now we express f in terms of basis, that is sum I fi ei. Now we apply this on the right hand side too, that is d by dt of express pre in terms of basis element sum j pj ej. So it's generally used to show how various indices are used. These are dummy indices. You can call them anything. It is time before we get rid of this summation using Einstein convention. Let's keep it for now. There is a differentiation taken of this summation. So what we have to do is pull in the differentiation. First term what we have is a dp by dt, that is a component, rate of change of component with respect to time, and the second term is a rate of change of the basis vector itself. Now in the earlier calculation we have assumed that the basis is a Euclidean, doesn't change with the time or the position, so we have set that to 0. Now we are using a little bit more complicated basis which might be changing from place to place, and then in such case the second term is not 0, and what we have is a basis element here We are not assuming it to be constant. So that's the main point here. Since the bases are vectors, their derivatives also should be vectors. If they are not vectors, then there is no way of handling them. So basic assumption is that the derivative of vector is also a vector. So once derivative is also vector, you should be able to express it in terms of the basis element. That is d e j by d should be also able to express it in terms of a basis element. This could be a function of both space and time, that doesn't matter. So in principle, you write the coefficient a, j, k, the jth element of the vector component, then you have a k, e, k. So that's basically written in terms of, it's always possible. Any vector can be expressed in terms of basis element. So that is what we do. Now we put it back everything. So this is the equation we started with. This is the first term. I just simply have pulled this out to keep this guy away. And the second term is what we are assuming, substituting this equation back in here. That is sum jk p j a j k into ek. So this is the equation what we have. Now look at this. These indices I, j, k, all dummy indices, they are summed over. They are not going to play any role. You can call them anything. Let's suitably rename them and rewrite the equation such that it's all become simple. So here we have I, here we have I, and here we have I outside, so that we can take the dot product with I and get rid of this and write down the component. Once we have this, the component equation looks something like this. F of I, force acting on a particle, is equal to rate of change of component of momentum plus momentum taken dot product with the AJI. So this is AJI tells you how the basis vector itself changes with the space and the time. So that is what is the extra term. This is a pretty peculiar. This extra term makes it a Newton's law is not a form invariant. So each time it may be different based on the what kind of basis you have. It may or may not be able to be written purely in terms of a quantity which is external force. So what we have is a term which depends on a coordinate system, and that is what makes the whole thing ugly. So that means Aij have to be 0 if the Newton's law is to be form invariant. That means we cannot use basis which depends on the space or time to express Newton's law. If we do that, the Newton's law does not become a form invariant, or the neat in the look same in the all coordinate system. So this is exactly is a Newton's first law of motion, again written in the mathematical form, which says that the basis element on which you express the Newton's law should be constant. Otherwise, it is all going to look different in different frame. So in other way, we have a two way of stating the Newton's first law of motion. One, we say that the particle remain at rest and moving at the uniform speed will move at the uniform speed in absence of force. Another way of saying that the basis element which we are used to represent the physics should have a constant values. Of course, we don't know. If we are going to use the bases which are not constant, then we got to make suitable adjustment. Now that is how you may think that we can make suitable adjustment. Yes, we can make it, and that is how we apply Newton's law in the polar coordinate and so on. So that's a story which will have to be done a little later. Okay, so with this idea, let's do a little bit further progress. So that is what we call integral curve and the tangent vector. So we have seen that the basis elements are playing a very important role in representing the vector spaces. Now we got to get to coordinate system in which laws of physics are applied. So the important relation between these two is what we call is an integral curve. Let T of x be a smooth vector field. This could be basis or it could be any other vector field. The integral curve of t is obtained by the solving the differential equation d gamma by dt is equal to t of x. So this is a first order simple differential equation. You solve it and then what you get is an integral curve for the vector field t. So that is what you say is you have a vector field which is present at every point in the space, and then you simply solve this equation, and then what you get is an integral curve. What does it mean? That this integral curve is such that the tangent of this integral curve is matches with the vector field. So this gives rise to other idea is that the tangent vector field. So if you have a gamma is a smooth curve, then the tangent vector for the curve gamma of t is given by t is equal to d gamma by dt. That is basically how you represent a tangent vector to the curve. So these two are a very connected concept which plays a very fundamental role in the differential geometry, and especially when the tangent vectors are the basis element. So let's quickly look at the idea of the basis vector and the coordinate system. For a given basis, the integral curve can be constructed and can be used as a coordinate system, and this is called the coordinate basis. So you have a basis vector, and then you simply find out the integral curve, and that is where you have is a coordinate system. You can do other way around also. If you have a coordinate system, then you can simply coordinate curves and construct the basis by simply taking the tangent vectors of those curves. Let's quickly look at an example. Let's take a two-dimensional space. You have a two Euclidean basis vectors, that is E1 is equal to 1, 0 and E2 is equal to 0, 1. It's a standard this thing. Let's compute the integral curve. The integral curve, first one is obtained, gamma 1 is equal to d by dt of E1. So you can simply integrate it. It is fairly straightforward. The first one you get is a gamma 1 as a two component x and y. So x is becomes t plus c1 and y, which is 0 here. So that becomes a constant, and the constant can be changed, and these are the set of straight lines. You can rename them, you can call them x, y and so on, and that is where you have the integral curves which are straight line. This is how you write the Newton's law in terms of the coordinate basis, where you have integral curve which are a straight line. When the basis vectors are constant, you are sure of having integral curves as a straight line, and that is what we needed for expressing the Newton's law. Otherwise, Newton's law is not form invariant. If the coordinate curves are not straight line, then simply you need an extra term in the Newton's law to show how the basis or coordinate curve themselves accelerate or change. That is how a correction is needed. So that is well within the scope of Newtonian mechanics. Newton's laws are form invariant only in the inertial frames where the basis vectors are constant. You have a two set of basis vectors, then you can naturally write the Newton's law and transform smoothly from one to another. Now same way we can integrate the second curve, that is for E2, that would also come as a gamma 2 as a C3 comma t plus C4. C3 and C4 are constant. This way you can construct a coordinate system for a given vector basis, or you construct a basis vector for a given coordinate system. So this is plays an important role. You can see that later you are going to do a curvilinear geometry where the curves are not going to be straight line and the basis vectors are not going to be constant every place. So classic example is your spherical polar coordinate system. So we will handle that as we go along. Let me stop now. We already have learned how to construct Euclidean basis, then construct Euclidean coordinate system. It all means that the Newton's law can be written, expressed in its standard form. This also means that these are Euclidean distances represents the inertial frame. That is where we are going to apply Newton's law. If you don't want to have a Euclidean distance, then you need to do suitable corrections for the Newton's law, and that is what we are going to do as we go along. Let me stop here and continue next lecture.